Also consider that this 1D domain has a cross-sectional area A, which can be a function of x. However, in this schematic, we are assuming that the area remains constant. Okay, so this is our cross-sectional area. Okay, in order to develop a partial differential equation, let's consider a small differential element, okay, of length dx. And let's zoom into that element. The width of this element is dx. At this point, our body force or distributed force is f of x. Consider a force on the left face as a big F, and on the right face is F plus small increment df. Okay. Now assume that this force is a function of x. Okay, so then we can write f plus partial of f with respect to x times dx. Okay, now consider force balance over the differential element. So then we have f plus partial of f with respect to x times dx plus f of x. Now the distributed force is defined per unit volume. So then times the volume, which is the length dx times the area A0. Okay, minus the force on the left face is equal to mass times the acceleration. Assume the density is rho of x. This is our density of the bar times the area times dx. This forms the volume, and acceleration is the second derivative of the displacement u with respect to time. Okay, simplifying this can get rid of the f, and from all the sides can also get rid of dx. Then we end up with partial of f with respect to x plus the cross-sectional area times the distributed force is equal to the density as a function of x times the area times the acceleration. Now consider the force term. Force is area times the stress, and since we are only dealing in one direction, we have one component of stress, which is sigma x. Okay, now from our constitutive relation we can write sigma as Young's modulus times the strain. Okay, which I can write as derivative of u with respect to x. Okay, now substitute this back into the above equation. We end up with partial with respect to x of a0 e partial of u with respect to x plus a0 f of x is equal to the density rho times a0 times acceleration. Now, assuming our area and the Young's modulus does not vary as a function of x, we can then write modulus times the second partial derivative of u with respect to x plus the distributed load is equal to the density times the acceleration. And this is our second order partial differential equation.